Dear organizer and participant, 7th International Workshop on Computer Modeling and Intelligent Systems, let me present paper Multi-Agent Reinforcement Learning Method with Dynamic Parameters for Logistic Tasks. Problem statement. Intelligent computer systems that are based on parallel and distributed computational play an important role in the planning of cargo transportation, in supply chain management, and auditing. One of the approaches to building such computer systems is the use of multi-agents. Currently, one of the main types of computer agents of multi-agent systems are proactive agents. Disadvantages of proactive agents. First, insufficient decision-making speed. Second, the complexity of organizing multi-agent interaction. Third, the complexity of the implementation of the perception function that maps signals from receptors into formulas in the language of first-order predicate logic. Fourth, the complexity of the formal description in the language of the first-order predictive logic of the dynamic environment. Purpose and research objectives. Purpose of the research is to create the methodology for construction proactive agents based on reinforcement learning to solve the problem of optimal planning of cargo transportation. Research objectives. Formalization of the proactive agents function. Propose models for functioning of proactive agents with the utility function based on reinforcement learning. Propose a multi-agent reinforcement learning method with time difference and dynamic parameters. Propose a multi-agent reinforcement learning method based on Monte Carlo and dynamic parameters. Propose a multi-agent reinforcement learning method based on adaptive dynamic programming and dynamic parameters. Material and methods. First, modeling the functioning of proactive agent with a utility function through reinforcement learning. Let a utility function U assign a utility to state and be presented as shown in the slide. Let there be a memory of reproduction experiment be represented next formula. Then, for proactive agent with a utility function, the procedure for generation an action plan P for the transition from the initial state as 0 to the target state as star models the planning function plane and is presented in the following form. First step, initialization. Second step, choice of action and observation of the internal state. Second step, termination condition. The work process reinforcement learning method based on adaptive dynamic programming. Second, multi-agent reinforcement learning method based on adaptive dynamic programming and dynamic parameters. First step, initialization, include next sub-steps present on the current slide. Second step, iteration number n equal 1. Third step, the parameters are calculated by next formulas. Fourth step, the number of the moment in time is set t equal 1. Fifth step, the initial state S kt is observed for each agent. Sixth step, For each agent action, A is chosen using the epsilon greedy policy P. 7th step, for each agent a reward R is calculated. 8th step, for each agent a new state is observed. 9th step, the transition function is calculated by formula and in advance by next formula. 10th step, for each agent the value of combination of the state action, cost function of the swarm and the agent is calculated by formula present on the slide. 11th step, for each agent the value of the cost function of the state action is calculated as present on the next slide by formula. 12. Step, calculate the value of the cost function of the state action of the swarm of agents for each agent in the form. Third, for each agent, the current state is set. 14. If the current time is not the last, then increase the iteration number, go to step 6. 15. If the current iteration is not the last one, then increase the iteration number and go to step 3. The numerical study of the proposed method was carried out using the Python package. For multi-agent reinforcement learning method, the value of parameters ρ1 min equal 0.1, ρ1 max equal 0.9, ρ2 min equal 0.1, ρ2 maximum equal 0.9. Control the learning rate parameter. Parameters epsilon min equal 0.1, epsilon max equal 0.9. Control the epsilon greedy policy. Parameter gamma min equal 0.1, gamma max equal 0.9. Control discounting. The number of agents is k equal 20. The dependence of parameter gamma n on iteration number n is linear and shown that its share increases with the iteration number. The dependence of parameter ρ1, ρ2 and epsilon on the iteration number n is linear. It shows that their share decreases with increasing iteration number. The result of compression of the proposed reinforcement learning method based on adaptive dynamic programming with dynamic parameters and the traditional passive adaptive dynamic programming method based on the mean square error criterion and the number of iterations for solving the traveling salesman problem. Berlin 52 standard dataset, which is used for freight planning, are presented in table 1 on the next slide. Table 1, compression of the proposed optimization method with the traditional passive adaptive dynamic programming method. Advantages of the proposed method. Modification of the reinforcement learning method due to dynamic parameter allows for an increase in the learning rate while maintaining the mean square error of the methods. Second, the use of multi-agent approach makes distributed computing possible and increases the learning speed while maintaining the root mean square error of the method. Third, reinforcement learning method with dynamic parameter use the epsilon greedy approach, which is called to random search, at initial iteration and close to directed search at final iteration. This is ensured by the use of dynamic parameters and allows for increase in the learning rate while maintaining the mean squared error of the method. Conclusions. First, to solve the problem of insufficient efficiency of computer agents, the existing method of statistical and machine learning were investigated. The studies have shown that to date the most effective approaches to creating proactive agents are reinforcement learning approaches. Second, the formalization of function of proactive agent has been conducted. Third, as part of creating a model for functional or proactive agent based on reinforcement learning, a procedure for generating a quasi-optimal action plan is proposed that models the planning function of proactive agent, which speeds up the decision-making process. Reinforcement learning methods are proposed, which at the initial iterations are close to random search and the final iterations are close to the directed search. This is ensured by the use of dynamic parameters and multi-agent approach and allows for an increase in the learning rate while maintaining the mean square error of the method. The proposed multi-agent method will be used for rate planning in the supply chain management and auditing and were investigated on a standard data set. Thank you for attention.